Welcome to this problem walkthrough. In this session, we'll tackle LeetCode problem number 14, longest common prefix. This is a classic string manipulation problem that tests your ability to work with arrays and find efficient solutions. Whether you're preparing for interviews or sharpening your coding skills, this problem is a great one to practice. Let's dive in. In this problem, you are given an array of strings, and your task is to find the longest common prefix shared amongst all the strings in the array. If no common prefix exists, you'll return an empty string. The input consists of an array of strings, where the number of strings is between 1 and 200, and each string can have a length ranging from 0 to 200. The output is a single string that represents this longest common prefix. For example, if the input array is flower, flow, flight, the output would be FL. This is because the first two characters, F and L, are common at the beginning of all three strings, while the third character starts to differ. The reasoning behind the first example is that flower, flow, and flight share the prefix FL, as the first two characters match in all three strings, but the third character is different. In another example, if the input array is dog, racecar, car, the output would be an empty string because there is no common prefix at all. The first characters of each string are already different, meaning no matching sequence exists at the beginning of these strings. Now consider the input, interspecies, interstellar, interstate. This is another interesting scenario with a different result. For this third example, the longest common prefix is inters. Here, the first 6 characters of all three strings match, but the 7th character differs. This highlights that the longest common prefix is determined by comparing characters sequentially until a mismatch is found. Along with these examples, there are constraints to consider. All strings in the input array will consist only of lowercase English letters, and the total number of strings in the array, as well as the lengths of the strings themselves, fall within the specified ranges. If the input array is empty or if all the strings in the array are empty, the expected output is an empty string. Let's also examine some edge cases to clarify further. In situations where all strings in the array are identical, the longest common prefix is simply the string itself. For instance, if the input is hello, 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 the output is hello. If the array contains only one string, such as single, the output is that string. When strings have different lengths, the prefix is determined by the shortest string. For example, with ABC, the output is a. Lastly, if there is no common prefix at all, such as in the case of apple, banana, cherry, the result is an empty string. These scenarios emphasize the importance of handling edge cases carefully while solving this problem. To tackle the problem of finding the longest common prefix among an array of strings, we can consider several approaches, each with its own strengths and trade-offs. The first method is horizontal scanning, which starts with the entire first string as the initial prefix. We then compare this prefix with each subsequent string, character by character, and reduce the prefix whenever a mismatch occurs. This approach is straightforward and works well for moderately sized inputs, but it can become inefficient if the strings are long or mismatches occur late in the comparison process. Another option is vertical scanning, where instead of comparing whole strings, we examine characters column by column across all strings. This continues until we find a mismatch or reach the end of one of the strings. While this method has a similar time complexity to horizontal scanning, it avoids unnecessary slicing operations, which can make it slightly faster in certain scenarios. Another strategy we can use is divide and conquer. This approach divides the array of strings into halves, finds the longest common prefix for each half recursively, and then merges the results. This method is elegant and scales well for larger inputs, but it comes with the overhead of recursion, making it less suitable for smaller datasets or cases where debugging is necessary. Lastly, we have the binary search method, which takes a different approach by focusing on the length of the prefix rather than the strings themselves. It uses binary search to determine the maximum length of the common prefix shared by all strings. Starting with the range between 0 and the shortest string's length, we iteratively check whether all strings share a prefix of the midpoint length and adjust the range based on the result. This approach is highly efficient for large input sizes due to its logarithmic search space, but it is more complex to implement compared to scanning methods. The chosen strategy for this problem is horizontal scanning, as it offers a balance between simplicity and performance for typical inputs. This method avoids the complexities of recursion and minimizes comparisons by stopping early when the prefix becomes empty. Some key observations make this approach particularly effective. First, if any string in the array is empty, the result is immediately an empty string. Second, the longest common prefix cannot exceed the length of the shortest string in the array. Finally, by iteratively shrinking the prefix, we ensure that we only perform the necessary comparisons, avoiding redundant checks. While horizontal scanning may not be as fast as binary search for extremely large inputs, its simplicity and efficiency make it a practical choice for most real-world scenarios. The algorithm itself is straightforward: initialize the prefix as the first string, then iteratively compare and reduce it with each subsequent string, stopping early if the prefix becomes empty. This solution effectively reduces the longest common prefix by slicing the prefix string whenever mismatches occur, ensuring that only the valid matching portion is retained. It handles edge cases gracefully, such as when the input contains empty strings or the prefix is eliminated entirely. Compared to other approaches, horizontal scanning stands out for its clarity and ease of implementation. While binary search offers better efficiency for very large datasets, it is more challenging to debug and implement. Divide and conquer, though elegant, incurs additional overhead due to its recursive nature, making it less suitable for smaller inputs. Vertical scanning, while equally efficient in terms of time complexity, can be less intuitive for some developers. Overall, horizontal scanning strikes a practical balance, delivering both clarity and performance without introducing unnecessary complexity. The problem at hand is to determine the longest common prefix among an array of strings. If there is no common prefix, we return an empty string. For example, in the array flower, flow, flight, the longest common prefix is FL. To solve this, we use an approach called horizontal scanning. The key idea behind this approach is to iteratively compare prefixes. We begin with the first string as the initial prefix and then progressively refine it as we compare it with each subsequent string in the array. This way, we ensure that the prefix is reduced to its smallest valid form as early as possible, avoiding unnecessary comparisons and improving efficiency. To implement the horizontal scanning approach, we follow these steps. First, there are some base cases to handle. If the input array is empty, we immediately return an empty string, since no prefix can exist. If the array contains only one string, that string itself is the longest common prefix. Next, we initialize the prefix by assuming the first string in the array is the longest possible prefix. From there, we iterate through the remaining strings in the array. For each string, we check if the current prefix is a prefix of that string using a method like starts with. If not, we repeatedly shorten the prefix by removing its last character until it matches the beginning of the string or becomes empty. If the prefix becomes empty at any point, we can conclude there is no common prefix and return an empty string. Otherwise, after processing all the strings, the remaining prefix is our result. This approach is efficient because of several key insights. First, we leverage early termination. If the prefix becomes empty during any iteration, we know no common prefix exists, so we can stop processing. Second, the iterative refinement of the prefix ensures that we only make the minimal necessary comparisons, avoiding redundant checks. Additionally, this method handles edge cases gracefully. For example, it works with an empty input array, an array with just one string, strings that share no common prefix, and even cases where all strings are identical. From a data structure perspective, this algorithm uses minimal resources. We maintain the prefix as a single string variable, which keeps our space usage low, and we directly work with the input array without introducing extra structures. Analyzing the complexity, the time complexity of this approach is n*m, where n is the number of strings and m is the length of the shortest string. This is because, in the worst case, we compare each character of the shortest string against all other strings. The space complexity is O(1), since we only use a single string variable to store the prefix. Let's consider an example to see how this works. Given the input, flower, flow, flight, we start with prefix equals flower. Comparing it with flow, we see that flower is not a prefix of flow, so we shorten it to flow and then flow, which matches. Next, comparing flow with flight, we find that flow is not a prefix. We shorten it to flow and then fl, which matches. After processing all strings, the result is FL. Now, let's look at an edge case where the input is dog, racecar, car. Here, we initialize prefix equals dog. Comparing it with racecar, we find that dog is not a prefix. We shorten it to do, then d, and finally. Since the prefix becomes empty, we return an empty string, as no common prefix exists. To optimize this approach further, we can limit comparisons to the length of the shortest string, since a prefix longer than that is impossible. Additionally, using built-in string comparison functions can help improve performance by leveraging optimized implementations. These small adjustments make the algorithm not just correct but also efficient and practical for real-world usage. This Python implementation solves LeetCode problem number 14, longest common prefix, using a horizontal scanning approach. The function begins by checking if the input list of strings is empty. If so, it immediately returns an empty string as the result. The algorithm initializes the prefix variable with the first string in the list. This serves as the initial longest common prefix. The function then iterates through the remaining strings in the list. For each string, a while loop ensures that the current prefix matches the beginning of the string. If it doesn't, the loop shortens the prefix by removing the last character until a match is found or the prefix becomes empty. If the prefix is reduced to an empty string, the function returns an empty string, as no common prefix exists. Finally, after processing all strings, the updated prefix is returned as the longest common prefix. This approach efficiently narrows down the prefix by performing comparisons over the length of the strings, ensuring an optimal solution for this problem. This is the Java implementation of the longest common prefix problem, LeetCode number 14. The logic mirrors the Python solution provided, starting with the first string as the initial prefix and iteratively comparing it with subsequent strings. Type declarations are explicitly handled in Java, and methods like starts with and substring are used for string operations. The solution handles edge cases, such as empty arrays, ensuring robustness. The class structure is also tailored to LeetCode's requirements, with the method signature matching the platform's expectations. To solve the problem of finding the longest common prefix, we start by making sure the input list, strs, is not empty. If it is empty, we would immediately return an empty string, but in this case, it contains 3 strings, flower, flow, and flight, so we proceed. Our initial step is to set the first string in the list, flower, as the prefix. This is our starting point for comparison. Now, we compare this prefix with the second string, flow. Since flow does not start with flower, we shorten the prefix by removing characters from the end. First, the prefix becomes flow, but flow still doesn't match. Shortening further to flow, we find that flow does start with this prefix. With a match found, we move on to the next string. Now, the prefix flow is compared with the third string, flight. Here, we see that flight does not start with flow, so we shorten the prefix again by removing one character at a time from the end. It becomes flow, but flight still does not start with it. Shortening further, we get FL, and now flight starts with this prefix. At this point, all strings in the list have been processed. The final longest common prefix, after all comparisons, is FL, which we return as the result. In this example, we have a different set of strings, dog, racecar, and car. As before, we ensure the input list is not empty and set the first string, dog, as the initial prefix. We start by comparing this prefix with the second string, racecar. Since racecar does not start with dog, we shorten the prefix to do and check again. It still does not match, so we shorten it further to d. Once again, there is no match, so the prefix is reduced to an empty string. At this point, since the prefix is empty, we can conclude that there is no common prefix among these strings. The function immediately returns an empty string, as the result. Here, the input list contains 3 identical strings, apple, apple, and apple. As usual, we first check that the list is not empty. Then, we set the first string, apple, as the initial prefix. Next, we compare this prefix with the second string, which is also apple. Since the second string starts with the prefix apple, no changes are needed. We then move on to the third string, again apple, and find that it also starts with the prefix apple. Since all strings in the list match the prefix, we have completed the comparisons. The longest common prefix in this case is the entire string, apple, which we return as the result. This algorithm follows a simple and efficient approach. It begins by using the first string as the initial prefix and compares it sequentially with the other strings in the list. If a string does not start with the current prefix, the algorithm shortens the prefix character by character until a match is found or the prefix becomes empty. If the prefix becomes empty during any comparison, we know that no common prefix exists, and the function immediately returns an empty string. The time complexity of this algorithm is O(s), where s is the total number of characters across all strings, as each character in the prefix is compared with each string. The space complexity is O(1), as no additional space is used apart from modifying the prefix variable in place. The time complexity of this solution can be broken down step by step, starting with the outer loop. This loop iterates through all the strings in the input list, excluding the first one. If there are m strings in the list, this outer loop will execute m1 times, contributing an O(m) factor to the overall complexity. Now, within this loop, we have the inner while loop, which is responsible for comparing the current prefix with each string. Here, the slicing operation and string comparison both take time proportional to the length of the prefix. In the worst case, the prefix is reduced one character at a time until it becomes empty. This means the total comparisons for a single string will take n time, where n is the length of the longest string. When we consider all the strings together, the total number of comparisons is proportional to the sum of the lengths of all strings in the input, which we denote as s. Therefore, the inner loop across all strings contributes O(s) to the overall complexity. Combining this with the outer loop, the total time complexity of the solution is O(s), where s represents the total number of characters across all strings in the list. Turning to space complexity, we analyze the memory usage of this solution. First, the input list strs is given to the function and does not require any additional space beyond its initial storage. Next, we have the prefix variable, which stores a substring of the first string in the list. The maximum space required for prefix is proportional to the length of the first string, which is O(n), where n is the length of that string. Beyond this, no additional significant data structures are used in the solution. Operations like slicing are performed in constant space. As a result, the overall space complexity of the solution is O(n), determined solely by the memory required for the prefix variable. To put this into perspective, let's compare the current approach with a brute force method. In a naive solution, we would compare each character of all the strings at the same position, iterating through all the strings character by character until we find a mismatch. This brute force approach would require O(m*n) operations in the worst case, where m is the number of strings and n is the length of the shortest string. However, the current solution improves on this by reducing the prefix iteratively. Instead of comparing characters individually, it compares substrings or prefixes directly. This optimization gives us a time complexity of O(s), which is more efficient than O(m*n) in scenarios where the total number of characters s across all strings is smaller than m*n. Considering the best, average, and worst cases, we can analyze the performance of this solution more clearly. In the best case, all strings share the same prefix, or the input list contains just one string. Here, the while loop terminates immediately for each string, and the time complexity is O(m), where m is the number of strings. In the average case, the prefix is reduced a few times for each string, leading to a time complexity proportional to O(s). Now, in the worst case, there is no common prefix among the strings. In this scenario, the prefix is reduced character by character until it becomes empty, resulting in the maximum number of comparisons and a time complexity of O(s). Mathematically, the total number of comparisons is proportional to the total number of characters across all strings, denoted as s. Each comparison and slicing operation takes linear time and the length of the prefix, and as the prefix length decreases with each iteration, the overall complexity remains dominated by O(s). This justifies the final time complexity of the solution as O(s). When tackling the longest common prefix problem, there are several common mistakes that you should be aware of. First, failing to handle empty input is a frequent oversight. If the input array is empty and you try to access elements without checking, it could lead to runtime errors. Similarly, single-element arrays are another edge case that can trip up your solution if not handled carefully. Second, assuming that all strings in the array are of the same length is another pitfall. Strings can vary in length, and this assumption can result in out-of-bounds errors during character-by-character comparisons. Third, using nested loops inefficiently is another challenge. A naive approach that compares each string with every other string can quickly become computationally expensive, especially if the input size is large. Fourth, modifying the input array directly can be problematic. For instance, sorting or altering the array might violate constraints or interfere with subsequent operations. If you need to make changes, always work on a copy instead. Lastly, overcomplicating the solution is a common issue. While techniques like recursion or divide and conquer can be powerful, they may introduce unnecessary complexity or inefficiency if not implemented with a clear understanding of their trade-offs. To succeed in interviews, it's important to recognize patterns and problems like the longest common prefix. These problems often involve repetitive comparisons of string prefixes, so optimizing for early exits is key. For example, breaking out of your loop as soon as a mismatch is found can save valuable time. Testing edge cases thoroughly is another critical step. Inputs such as an empty array, strings with no common prefix, or strings that are all identical are important to cover. In terms of approach, iterative solutions like horizontal scanning are usually preferred in interviews because they're easier to explain and debug. Recursive solutions, such as divide and conquer, can make a strong impression, but only if executed efficiently and clearly. Space complexity is another factor to keep in mind. Most interviewers expect solutions to use one additional space unless otherwise specified. Keeping these insights in mind will help you craft a solution that is both robust and optimized for the interview setting. The longest common prefix problem is closely related to other problems that you might encounter. For instance, LeetCode number 28, implement strstr, involves substring searching and requires character-by-character comparisons, making it conceptually similar. LeetCode number 720, longest word in dictionary, also uses prefix logic but adds the complexity of working with a dictionary and sorting. Additionally, LeetCode number 242, valid anagram, shares a focus on string manipulation and comparison. Even LeetCode number 5, longest palindromic substring, while not directly related, requires a similar mindset for efficient string processing. Now, when it comes to alternative approaches to solving the longest common prefix problem, one of the most common is horizontal scanning. This method involves comparing the prefix of the first string with subsequent strings and updating the prefix as you go. It has a time complexity of n*m, where n is the number of strings and m is the average string length, and it uses one additional space. While this approach is simple and intuitive, it may become slow if the number of strings or their length increases significantly. Understanding these related problems and approaches can help you build a broader toolkit for solving similar challenges. Another approach to solving the problem is vertical scanning, which involves comparing characters column by column across all strings. This method stops as soon as a mismatch is encountered, making it efficient for identifying early exits. Its time complexity is n*m, and it uses one additional space, but you'll need to handle boundary conditions carefully. Divide and conquer is another strategy you can use. In this method, you recursively divide the array into halves, find the common prefix for each half, and then merge the results. This approach has the same time complexity of n*m, but it requires log n space due to recursion. While it's elegant and can be efficient, it's more complex to implement and debug. Finally, binary search offers a unique angle. Here, you test the prefix length using binary search and validate it against all strings. This method has a time complexity of n*m*log m and uses one space. It's particularly effective for longer strings but may be harder to implement under time pressure. Each of these approaches has its own trade-offs, so it's important to choose the one that best suits the specific problem constraints and context. Great job! In this session, we explored the longest common prefix problem and discussed multiple approaches to solve it efficiently. Remember to practice handling edge cases and consider the trade-offs between simplicity and performance. Thanks for watching, and don't forget to like and subscribe for more content. Keep coding and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!